All right, welcome you guys. So we're going to continue a few more theorems in this section. We did factor theorem and remainder theorem last time, and we're going to learn a couple more, and we're going to continue to use that polynomial division, whether it be synthetic or long division, and the other things we've learned throughout the class, like factoring by grouping, factoring with the trinomial, taking square roots, quadratic formula. So this is a great section to kind of review everything we've been doing. Okay. All right, so this first theorem, the fundamental theorem of algebra, says that every polynomial of degree n with n greater than or equal to 1 has at least one zero in the set of complex numbers. And typically this corollary is actually something we've been talking about in class a lot, which says if we include complex zeros and multiple zeros, then an nth degree polynomial has exactly n zeros. So you've heard me say that if you have an x to the fourth as your highest exponent, then you know that you should get 4 answers if you include multiplicity. Okay, so that's been a way to check to make sure you found all the zeros. If it's degree 3, do you have 3? Okay, and so we've actually been using this corollary quite often throughout the class. Okay, it says write a degree 3, a polynomial of degree 3 that has the zeros 2, which has multiplicity 2, and -5. Verify your answer with the graphing utility. So this is actually the reverse of what you've been doing a lot throughout the semester. So throughout the semester, you might take something like, let's just do x squared minus 4x plus 3, okay, equals 0. We factored this, and I'm just going to tell you it's -3 and -1. And then we set each piece equal to 0, right, to get the following solutions, okay? Well, what we're doing is we're going to do the same thing, but in the opposite order. We're going to start off with the zeros. We're going to put them into the parentheses, changing their signs. And then we're just going to, FOIL this out, distribute this, and get back to the polynomial. So it's the process you know very well, just in the backwards order. So they're saying, okay, here's your zeros. We have a 0 of 2, but they told us that it's multiplicity 2, so I'm going to write it twice. And then we also have -5 as a 0. So if those are my zeros, then the parentheses that got me those zeros must have been x minus 2, x minus 2, and then x plus 5. Because remember, when you take them out of the parentheses, when you set them equal to 0, the sign changes, right? So now we're going to go ahead and just FOIL this out, and that's going to give us a polynomial of degree 3 with these zeros. So I'm going to start with FOILing out these first two. Oops. I'm combining the middles. Now I'm ready to take this polynomial and multiply it by x plus 5. Distributing the -4x. And then distributing the 4. Now we're going to go ahead and combine like terms. So that's going to get us just an x squared. -20 plus 4 is -16. And we'll give it a name. We'll say f of x, our generic, f of x. Okay. So this says verify this answer with the graphing utility. So what are we looking for in our answer? We see that this has multiplicity 2, which means that we should be tangent at x equals 2. And then we should cross at x equals -5. So let's go in and see if that's true when we go to graph this. All right, so the polynomial that we came up with is x to the 3rd plus x to the 2nd minus 16x plus 20. All right, and so we said that we should be, let's shrink this down a little bit, you guys. There we go. So we said that the zeros were -5 and 2. We said we should be tangent at 2 because it had an even multiplicity, and we should cross through -5. So this is exactly what we were hoping. Let me just come in here and get a little screenshot. All right, so this is exactly what we want. Okay. Now it does say write a polynomial. It turns out you could have infinitely many polynomials here. If we just went in and did any sort of multiplier by the front, so let's say that we take this exact same polynomial, but out front, we're like, you know what? I feel like putting a negative out front. Well, from what we know and earlier in the class, that's just going to reflect this across the x-axis. So when I hit enter, it just flips it, but it still has the same zeros. It still goes through -5 and is tangent at 2, right? Okay. And we could put a half out front to give it a vertical shrink. And so this will be half as high, but it'll still have the same zeros. Okay. So that's what they mean by write a polynomial. It turns out there's infinitely many polynomials that could have these zeros and with the given multiplicities. All right, let's kind of talk about a theorem that, or two theorems that we're going to use quite often throughout this section. Okay. So the imaginary zeros theorem. If the imaginary number a plus bi is a zero of a polynomial function with real coefficients, then a minus bi is also a zero. So we've seen stuff like this quite often in the class. Just to give you some instances where we've seen it, we've solved stuff like this in the class, where we move the 4 over, making it a -4, and then we square root. Let me say, don't forget your plus or minus, and there's going to be an I, and the square root of 4 is 2. Notice we couldn't get 2i without also getting -2i because of the plus or minus. Other instances where we've had situations like this would be maybe something like we've done the quadratic formula, right? And the quadratic formula, let's say it got us this. Okay. Well, we know that because there's a negative under the root, that it's going to be an I, and the square root of 49 is 7. So what this is, if we split it up, is -5 over 2 plus or minus 7i over 2. So notice we can't get -5 plus 7 over 2i without also getting -5 minus 7/2i because of the plus or minus in the quadratic formula. Okay, so this just shows that we'll always get the conjugates, right? If we get 1, we'll get the conjugate of it. If we get 1, we'll get the conjugate of it. Remember, don't change all the signs. It's just the sign on the I. Okay. Well, the same thing holds true of irrational numbers for the exact same reasons, you guys. I could just go in here, make a few tweaks, make this guy a minus. No, sorry, need more tweaks than that. Let's make this guy a 5. Okay. When we add the 5 over and we square root, we're going to get plus or minus. I can't get positive root 5 without also getting negative root 5. These irrationals come in pairs. Same thing with the quadratic formula, right? We could have done the quadratic formula, and let's say we ended up getting, when everything was simplified, I don't know, -2 plus or minus is inside the quadratic formula, right? Okay. And so something like that. So we can't end up getting, we can't get -2 plus root 6 without also getting -2 minus root 6 because of, again, the plus or minus of the quadratic formula. So the takeaway from this is that imaginary roots or zeros come in pairs, and irrational roots also come in pairs. So our first question says, suppose that a polynomial function has the zeros -5, 3 plus 2i, and negative root 7. Okay. So a lot of students will say, okay, if x equals -5 is a root, then so is +5. Well, that's not true. Remember, this is not imaginary or irrational, and so it doesn't come in pairs. We've often got -5 as an answer without getting +5, okay? So for this one, we're not going to get any additional root, since it's not imaginary or irrational. All right, but we will get some additional roots from these other two, okay? So 3 plus 2i can never be a root by itself. Its conjugate buddy, 3 minus 2i, is also a root. And then we can't get negative root 7 without also getting positive root 7, because irrational numbers also come in pairs. So those are going to be our additional roots here. Find a polynomial function of lowest degree with integer coefficients that has the following zeros. So now we're actually putting example 1 and example 2 together. Okay, we have the zeros 2/3 and 1 plus I given to us. Well, that means then that 1 minus I is also going to be an additional root because of imaginaries coming in conjugate pairs, right? So you just have to know this is an additional root. They are not going to advertise it. And then we know that we put these back into the parentheses, change their signs when we put them back into the parentheses. So a -1 and a negative I. For the last root, a -1 and a positive I if we change the signs. Now the directions do say that we want integer coefficients. Rarely has this shown up in the class, if ever. So integer means that we can't have fractions here. So we're just going to multiply by 3 to get, and we canceled the 3's here, right? So we end up getting the following. We get 3x minus 2. And when you think about it, that's probably something that we've set equal to 0 in the class many times, right? Move the 2 over and then divide by 3, right? So that's going to get you your 2/3, the way that we're used to seeing it. All right, so now we've got to multiply these out. And you want to make sure that you multiply these first, because what's going to happen is you're going to get rid of the imaginary numbers, and it'll make your life a lot easier. Okay, you could do it the other way, but it's just going to make your life pretty hard. You know, I'm not even going to bring this guy down. We'll bring him down when we need to. All right, so we're going to go ahead and multiply. So we got x times x for x squared, negative x, ix, negative x, positive 1, negative I, negative ix, positive ix, negative I squared. We're going to clean this up. We can see that we have an ix and a negative ix. We can see that we have, oops, I think I've made a mistake somewhere, you guys. Let me just double check. X times x is x squared. X times -1 is negative x. X times I is ix. -1 times x is negative x. A -1 times a -1 is positive 1. A -1 times x is negative I. That looks good. Negative ix. Right here, it should have been positive I. So it's good to know all the i's should go away, you guys. Wow, it helped me find a mistake, right? Okay, so now I'm going to go ahead and take this negative I and this positive I and cancel those. And then don't forget that I squared is -1. So this is actually -1. So that means it's going to become a +1, right? So we've got x squared minus 2x. And then I'm going to go ahead and take this positive 1 right here and this positive 1 right here to give me +2. All right. Now don't forget, this has to get multiplied by 3x minus 2. So we've got 3x cubed minus 6x squared. I'm going to go more slowly. Plus 6x minus 2x squared plus 4x minus 4. And I'm going to combine like terms. So I'm going to start off with my x cubed. Then I'm going to go ahead and take all my x squareds and combine them. I'm going to take my x to the first. And then finally my constant, which is just -4. And let me just check with work these out ahead of time. Just want to make sure. Yes, that matches. We're going to give it a name, f of x equals, there we go. So go slowly, and let's recap the process here. If you're ever given an imaginary number, like 1 plus I, then or irrational, then you know that its conjugate buddy has to be a 0 also. So we had to write this 1 minus I. We change the signs when we put them into the parentheses. Then we can't have fractions, so we multiply through by the denominator to eliminate the fractions. Okay. All right, and then we made sure we multiplied the stuff with i's first, because all of the i's should go away. Okay. Then once you've done that, distribute, make sure you're being very careful. Boom. There's our polynomial that will have these zeros. All right. So we're going to take a look at the rational zeros theorem, and I'm just going to kind of describe what's going on, why this works, how to use it. So let's say that we're given some sort of polynomial. So I'm going to give you one that we would already know how to solve, only for simplicity purposes. Honestly, we would be using this on degree 3 or higher. Degree 2, I mean, we have the quadratic formula. Okay. But I'm using a degree 2 to kind of help you see it better. But usually we'd use this on degree 3 or higher. Now, what this theorem says, it says that if there's going to be a rational zero, now remember, we're not guaranteed a rational zero. This might not factor, and I might use the quadratic formula and get some irrational numbers or some imaginary numbers from the quadratic formula. But if it does have a rational zero, okay, then we can find that rational zero by taking factors of the last number, a sub 0, over factors of the first number. Okay, so that's basically what it's saying. So let's talk that out. So we're going to look for factors of -5. So factors of -5, well, 1 and 5 are the only factors. Sorry, guys, the board's glitching. There we go. And then the front number is 2. The only factors of 2 are 1 and 2. Now let's talk about why I put plus or minuses on all these, okay? It's a -5, but we don't know what got us -5. Maybe it was -1 times +5, or maybe it was +1 times -5. So if we're looking at the signs here, the 5 could be positive or negative. The 1 could be positive or negative, right? So that's why we're putting a plus or minus on these factors. Same thing's true of 2. Okay, I know it's 2 times 1, but was it +2 times +1? Or was it -2 times -1? Because that's also going to be 2. Okay. All right, so that's why we're putting plus or minuses on all of these factors. We're not quite sure what the sign was, okay? Then basically you're just going to stack these numbers on top of each other, okay? So we're going to put 1 and 5 over the 1. So 1 over 1 is 1. And 5 over 1. And you know what? Just because it's our first time around, you guys, I'm going to write it out so you can see it. Oops. Let me turn my phone off really quickly. Sorry about that. Okay. So we're going to put 1 over 1. We're going to put 5 over 1. Then we're going to put 1 over 2. And we're going to put 5 over 2. Okay, so basically you're saying, all right, 1 over 1, 5 over 1. 1 over 2, 5 over 2. You didn't have to do it that way. You could be like, okay, 1 over 1, 1 over 2, 5 over 1, 5 over 2. It doesn't matter, you guys, what order. So what this tells me is this says reduce all your fractions. So 1 over 1's 1, 5 over 1's 5, and then a half and 5 halves, right? Okay. These are all of our possible rational zeros. If there's going to be a rational zero, right? All right, so let me do this the old-fashioned way to show you that this works, okay? So the old way that we would have done this, or the way we would do it normally anyways, is we would have taken this 2x squared plus 9x minus 5, and we would have factored it. We probably would use the AC method on this. So 2 times -5 is -10, right? So we're looking for things that multiply to make -10, but add to make the middle number of 9. So that's got to be 10 and -1. 10 times -1 is -10. 10 plus -1 is 9. All right, so we're going to go ahead and use factoring by grouping. So let's use the 10 and the -1 to rewrite just the 9, right? And then factoring by grouping. We're going to slice this guy down the middle. It looks like we can take out a 2x from both of these terms. 10 divided by 2 would be 5. And we're going to have to take out a -1 in order to make the signs change on this second term here. All right, so now these match, right? So we got x plus 5, and the leftovers are 2x minus 1. And I'm going to set it equal to 0 to find the zeros. So this would get me -5. And when you set this equal to 0, you guys, let me actually do it so you can see something. When I have this, it's actually the back number that's going to end up on the top of the fraction when I divide by 2. So hopefully that you can see that. The back number, the last number, goes on top. The front number goes on bottom. That's why when we were setting these up, we were saying, all right, factors of the last number are going to go on top. Factors of the first number are going to go on bottom, because that always gets people. They end up putting factors of the first one on top and factors of the last one on bottom. But you can see when we do the math over here, right? It's the last number that ends up in the top, and it is the front number that ends up in the bottom. Now, what I want you to see is these solutions that we got, these two solutions, are actually on our list of guesses. Yes, -5 was on our list, right? -5 was right here. Yes, +1/2 was on our list. +1/2 was right here. So this is giving us our possibilities. We're going to have a way to narrow it down, but it's like, hey, if we're going to have a rational zero, it's going to be one of these. So hopefully you kind of understand why the factors of the last go on top and why the factors of the first go on bottom, and how this whole process is going to end up working for us. So we're going to couple this together with what we learned in the last section, which is, okay, now that we know that these are our possible zeros, we're going to do synthetic division with them. And if we get remainder 0, it's a 0. If we don't get remainder 0, it's not a 0. So we'll be using the remainder theorem that we learned last section. Okay, so let's put it all together. So this first one just wants us to list the possible rational zeros. It does not need us to go in and find them, okay? So we're going to put factors of the last number. So we're going to put factors of -15 on top, and then we're going to put factors of the front number 4. So all the things that multiply to get us 15, right? 1 times 15 and 3 times 5 are the only ones I can think of. For 4, it could be 1 times 4, or it could be 2 times 2, right? So now we have to stack all of these on top of 1, right? All of these have to get stacked on top of 1, which that's just going to get them themselves back, right? If we have 1 stacked on top of 1, 15 stacked on top of 1, 3 on top of 1, those are all just going to get us the numbers themselves back. Okay, so I'm just going to go ahead and write them down as whole numbers. 1, 15, 3, and 5. That was us stacking them all on top of 1. Now we have to stack them all on top of 4. So 1 over 4, 15 over 4, 3 over 4, 5 over 4. Now we have to stack them all on top of 2. So 1 over 2, 15 over 2, 3 over 2, and 5 over 2. So these are, now if you can reduce, you must reduce, right? It turns out that none of these reduce, you guys, but quite often we'll have some that will reduce and they'll match a zero that's already there or a possible zero. And so you'll have to cross that off the list, but do make sure you reduce. So these are our possible rational zeros. Ooh, that's a big list, man. Hate to check those with synthetic division. All right, now we're just changing the directions to add a little bit more. It's saying now actually find the zeros, okay? So we're going to go in and we're going to list our possible rational zeros by putting factors of the last number. So factors of 3 on top of factors of the first number. So factors of 2. So all the things that multiply to make 3 are just 1 and 3. And then all the things that multiply to make 2 are just 1 times 2. So if we put all of these on top of 1, we'll just get themselves back. But then we're going to put all of those on top of 2. So 1 over 2, 3 over 2. So what we have found here are possible rational zeros. But now we need to go in and find out which ones are actual rational zeros, right? So these are possible rational zeros. Okay, so now we're going to go ahead and do some synthetic division with them. Okay, and I always like to do my whole numbers first because, you know, I'm putting those fractions off till the end. I might not have to do them. So I'm going to try 1. So exponent check 4, 3, 2, 1. All of our exponents are there, so I don't need any zeros in my synthetic division. So let's go in and see if the remainder is 0. If the remainder is 0, then it's a 0. 1 times 2 is 2, add together. 1 times 3 is 3. Negative 5 plus 3 is negative 2. 1 times negative 2 is negative 2, add that together. And 1 times negative 3, oh my goodness, we got so lucky. So since the remainder was 0, it is a 0. Now, I don't really want to continue doing synthetic division because I could do the entire list and none of them could work. Nothing guarantees that I'm going to get any more rational zeros. Maybe the rest of my zeros are irrational. Who knows? Okay. What I'm going to do is I'm going to try to factor or use some other skills we've learned in the class. So let's look at the remaining polynomial. The polynomial that remains from these coefficients has to be to the 3rd power because we started off with an x to the 4th. And remember, you always down it by 1. So this would be an x to the 3rd that would be remaining. So I'm going to go ahead and put the x's back. This is the polynomial that would remain. And I'm looking at that and I'm thinking, do I have to keep doing synthetic division? I don't. I can see that if I use factoring by grouping, that's going to turn out pretty nice. Okay. So I'm going to take out an x squared from the first 2 terms. And I'm going to take out a negative 1 so I can change the signs on these 2 terms because I want this term to match that one or that factor to match that one. So we've got 2x plus 3. That's multiplying by x squared minus 1. And x squared minus 1 could continue to factor. It's a difference of squares, so x plus 1 and x minus 1. So if we do the math here, where we set this equal to 0, let me actually do that for this one. I mean, I think you guys are to the stage to where we can probably do it in your head. We'd move the 3 over and it'll be negative. And then we'll end up dividing by 2. So we end up with x equals negative 3 halves, right? And then these, you can just clearly see, change the sign. It's going to be, actually, so it's going to be x equals negative 1. And then for this one, x minus 1 equals 0. So it's going to be positive 1. Okay, so let me go in and make sure I've answered the question. Find the zeros. All right, so let's go ahead and answer that. The zeros are, well, remember, 1 worked. Negative 3 halves and get this guy out of the way. -1, right? Okay, so let me clean this up. Let's see. The zeros are -1, -3/2. Let's put after this -1 with multiplicity 2. All right, maybe I'll put that in parentheses. There we go. All right, because look, we got 1 twice, right? We got 1 here, and then we got 1 again here. So we ended up getting 1 twice. So that's why we said it has multiplicity 2. And the reason why I'm stressing that is because we know that it's a degree 4 polynomial. So we should have 4 answers. So 1, 2, or double counting it because of its multiplicity, 3, 4. Okay, so that's going to answer the first question where it says, what are the zeros? Now it says to write the polynomial as a factor of linear factors, or factor the polynomial into linear factors. So whatever the zeros are, they need to go into the parentheses with their signs changed. So we got -1 twice, right? Because it was +1 here. And then we've got -3/2, so +3/2. And we got -1, so +1. So we basically just took all of our zeros and changed their signs when we put them into the parentheses. Now, we're going to clean this up. A couple ways we could clean this up, right? Number one, that x-1 that we have twice, we are going to write that as x-1 squared. Okay? Then we're not allowed to have integer coefficients. So we're going to multiply through by the 2, the denominator, to get a better version of this. Now we have our polynomial written as a product of linear factors. Now the question says which of the zeros are rational? In this case, all of them were. 1 is rational, -3/2 is rational, and -1 is rational. So we'll say all of the zeros are rational. Okay. All right, it's our first one. This should be like terrible. You should be like, what is going on? Okay. As we do more and more examples, things become clear, okay? All right, let's try another one. Same exact question, okay? Same exact directions. All right, so we're gonna start off by writing out what could be the possible rational zeros. So we're gonna need the factors of the last, which is -5, over the factors of the first, right? Which in this case is 1. So ±1 and ±5, 1 times 5 is 5. And 1 times 1 is 1. So if we stack these, 1 over 1 is just 1, and 5 over 1, that's just 5. So these are our possible rational zeros. We're going to try some synthetic division with these, and let's see what happens. Exponents, 3, 2, 1. We got them all. So we don't need any zeros when we put these in here. I'm going to try 1. Let's see what happens with 1. Let me write the coefficients down. All right, I'm going to bring down 1. 1 times 1 is 1. Add downward. 1 times -1 is -1. Add downward. And 1 times -15 is -15. We do not get a remainder of 0. Okay, so 1's not a 0. Why don't we try -1? -1 times 1 is -1. Add downward. A negative times a negative is positive. Add downward. Negative times a negative is a positive. Okay, again, we don't get remainder 0. So -1's not a 0. Let's try 5. Five times 1 is 5. Gets us 3. 5 times 3 is 15. That gets us 1. And 5 times 1 is 5. Ah, there it is. So this tells us that 5 is one of our zeros, right? Okay. Now, if we look at the polynomial that remains, and we put the x's back, in other words, right? Then this is going to be 1x squared. Now, why is it x squared? It started off as an x cubed, and we always go down by 1, right? So this is 1x squared plus 3x plus 1 that we're going to set equal to 0. And I probably, when I bring this up over here, will not write the 1 in front. Okay, so let me just arrow. So this is x squared plus 3x plus 1. Now we're going to use the quadratic formula, okay? This doesn't factor. There's no factors of 1 that add up to 3. So we're going to use the quadratic formula. All right, so x equals negative b, so negative 3, plus or minus the square root of b squared, so 3 squared, minus 4 times a, which is 1, and times c, which is 1, all over 2 times a. Nine minus 4, and 2 times 1 is 2. So it's going to be the square root of 5. So if you look at this, we really have negative 3 over 2 plus or minus root 5 over 2. Okay. So if we wrote that out the long way, that'd be negative 3 plus root 5 over 2 and negative 3 over 2 minus root 5 over 2. So let's go ahead and answer the question. The question says, what are the zeros, right? Well, don't forget, not only do we have these two right here, but we also have this 1. So our zeros are going to be 5. And I'm just going to write it like this, you guys, for this answer. Oh, there we go. All right, now to write it as a product of linear factors. So remember, you change the sign when you put the zeros in. So this 5, it's really going to be x minus 5. Okay. And I split these up on purpose. I'm going to change the signs on these. So this is going to be x plus 3/2. So I'm changing the sign on this 3/2 right here. And this plus sign will become a minus sign. So we're changing the signs. Same thing's true about this factor. It's going to be x plus 3/2. And we're going to change the sign on this minus root 5 over 2, and we're going to make it plus. Now we've written it as a product of linear factors. Now it says, which of the zeros are rational? Well, not all of them this time, because square root of 5, right? The square root of 5 here is making these two irrational. So the only rational zero in this case is going to be 5. Any square root that you can't, that's not a perfect square, that's going to end up being an irrational number. Okay. All right, we're given one of the zeros, and that's supposed to help us find the others. Thank goodness, because look at this polynomial. We have nothing that we could use on this right now, right? That's just gigantic, okay? All right, so we're going to reduce it down by using the 1 0 that they gave to us, the one solution. So negative 1/2 is going to go in the box, and we're not missing any exponents. So I'm going to write the coefficients of the polynomial down. Okay. Now we already know, you guys, that the remainder should be 0 because they told us this is a solution, aka this is a root, aka this is a 0, right? So we better get that when we do the math. Now I don't like get too technical with this. When usually it works out for me to just go, okay, what's the sign? A negative times a positive is a negative. And then I'll literally take half of 2. So half of 2 is 1. Then we add downward. Now I'll look at the signs. A negative times a negative, that's going to make this positive. and half of 2 is 1. I'm going to add down 1. A negative times a positive is negative, and half of 18 is 9. Add down 1. A negative times a negative is positive, and half of 18 is 9. And look, it worked. Okay, they don't usually give you terrible ones, I've noticed in most textbooks. So it's okay to just be like, well, what's half of that? All right, so I'm looking at that and I'm going, I don't want to keep doing synthetic division. I can see that that's going to be pretty nice if I go and I put the x's back. So it was degree 4, so now it's degree 3. So let's go and put those x's back. All right, so we're going to slice this guy down the middle, and we're going to use factoring by grouping. So we're going to pull out a 2x squared from the first 2. And then we're going to pull out an 18, factor out an 18 from the second 2. This is good news. So we're going to factor out x minus 1, and that's going to leave us with 2x squared plus 18. Now we can't factor the 2x squared plus 18 as a difference of squares because it's a plus sign, okay? So I'm just going to go ahead and set them equal to 0 now. There's other stuff we could do, like take out the 2, but we can just set it equal to 0 right now. So I'm going to move the 18 over, so it's negative. Then I'm going to go ahead and divide by 2. That's a nice number. So x squared equals negative 9. I'm going to root to get rid of the x squared. Don't forget your plus or minus whenever you root. Okay, there's a negative under the radical, so I know it's going to be an I. The square root of 9 is 3, so this is going to end up being 3i. Okay, so given that negative 1/2 is a solution, find the remaining solutions. Okay, so these are what I would classify as the remaining solutions. Okay. Let's just do this 1, comma, 3i, and negative 3i. Oops. And all right. Given that I is a 0, find the other zeros. Okay, so again, we already know that if we put I in the box and we do synthetic division, we should get a remainder 0 because they told us it's a 0. So let's go ahead and write the coefficients. I notice that all the exponents are here, 4, 3, 2, 1, and none. So we're going to go ahead and write out the coefficients. All right, so I times 1 is I. We cannot combine those because they're not like terms, so I'm just going to write negative 5 plus I. Now we're going to multiply I times this negative 5 plus I, right? So that's going to get us negative 5i plus I squared. But remember, I squared is negative 1, so it's going to get us that. All right. Let me just make sure I'm writing down everything correctly. Yeah. Looks good. All right. So then that's going to be right here, right? All right. So we're going to combine the like terms. These are our like terms right here, right? So then we're going to have the negative 5i that gets brought down plus 6 when we combine what we see in red. So now we're going to have to multiply I times that. So underneath this, let's go ahead and do it in blue. I'm going to do I times negative 5i plus 6. So that's going to get me negative 5i squared plus 6i. Well, we know I squared is negative 1. So when we do negative 5 times negative 1, it's actually going to be positive 5. So we got 5 plus 6i. We're going to combine the like terms, which is very nice. Those are going to go away, right? So we just have 6i. So we have to multiply I times 6i. Well, that's just 6i squared, or 6 times negative 1. So it's going to be negative 6. Whew. We got remainder 0. That's your built-in check. You don't get remainder 0, then you know that you did something wrong, right? Okay, now look at this, what's left. We got all these coefficients that are terrible. I don't want to put a polynomial back, right? So remember we learned the very first thing, maybe it wasn't the first thing, but we learned in this section that imaginaries come in pairs. If I is a 0, then its conjugate, negative I, is also a 0, right? Okay, so we're going to divide through now by negative I, and we already know that when we get done, we should get remainder 0. All right, so negative I times 1 is just negative I. If we combine the like terms, those will cancel, so we'll just get negative 5. A negative times a negative will make this positive 5i. Again, look how nice this is. The second time around is so much easier, you guys. So just the 6 survives. And then negative I times 6 is negative 6i. There's our remainder 0. Now this, I'm willing to put the x's back, right? So now we've actually divided twice. We divided by I to give us x to the third. We divided by negative I to give us x to the second. So this is going to be 1x to the second minus 5x plus 6. That's our remaining polynomial. So we've already found, well, we already knew 1, 0. Now we have another 0. And look at how easy this polynomial that remains is. This 6, we factors of 6, things that multiply to make 6, that add to make the middle number. Negative 3 and negative 2. A negative times a negative equals a positive. A negative plus a negative stays negative. So this will factor as x minus 3, x minus 2. So when we set these equal to 0, we get 3. And when we set this one equal to 0, we get 2. So it says find the other zeros. Well, before we even started, we should have known negative I, right? Okay. Since I is a 0, negative I has to be a 0 also. So the remaining zeros are negative I, 3, and 2. All right, so we use that irrational zeros theorem that we learned towards the beginning of this section. Okay. All right, you guys, I think, does that do it? No, we have one more. Okay. All right, in this one, we want to do it 2 different ways, it says in the directions, okay? So let's do it how we just did it a second ago, right? It says find the zeros. Well, we know 2i is a 0. So we're going to do synthetic division with 2i. Now notice a lot of terms are missing, right? We are going to have to put a 0 in for the x cubed, a 0 in for the x squared, a 0 for the x to the first. Holy moly, that's a lot of zeros. So it'd be 1, 1, 2, 3 zeros, and then finally our 16. So 2i times 1 is 2i. 0 plus 2i is 2i. 2i times 2i gives us 4i squared. Well, 4 times negative 1 is negative 4. And we're going to add downward. 2i times negative 4 is negative 8i. Add downward. So now we have to do 2i times negative 8i. So 2 times negative 8 is negative 16. I times I is I squared. So negative 16 times negative 1, that's positive 16. Oh, we knew it was going to be 0. So that is looking good. Now remember, if 2i is a 0, so is negative 2i. So we will just do synthetic division to that. And the second time is even easier. Negative 2i times 1 is negative 2i, so we get 0. Anything times 0 is 0, so we get negative 4. A negative times a negative is a positive. There it is. All right, so the remaining polynomial that we would get, remember it was x to the 4th. We divided once to get x to the 3rd. We divided twice to get x squared. So this is going to be 1x squared plus 0x take away 4. The 0x term, we don't need to write that. The 1, we don't need to write that. So this is the polynomial that remains. So we could just add the 4 over or factor the difference of squares. It's your call. Plus or minus 2. So here's our solutions. We have plus or minus 2i if you look up here, right? But we also have plus or minus 2 as well. So this one says, what are the zeros? So I'm going to write all of them down. It doesn't say what are the remaining zeros. So that was one way to do it. Okay. An alternative way to do it I think it's a little bit faster. It's kind of cool that these match though. So another way to find the zeros of x squared or x to the 4th, sorry, minus 16 is to look at that and go, man, that looks like a difference of squares. And it totally is a difference of squares. I don't think in this class we factored one with an x to the 4th, but we have if this was like an x squared, right? Well, it's the same concept. We know that it's got to be a plus and a minus. We square root the last number, so it must be 4 and 4. The only difference is I have to put x squareds here in order to make it multiply to get me x to the 4th. Like if I multiply these, I will get my x to the 4th, okay? So that's the only difference. Then we'll just simply set each piece equal to 0. And you could factor the difference of squares there if you wanted to. So we get x squared equals negative 4. When we go in here and we square root both sides, don't forget your plus or minuses. X equals plus or minus, it has to be an I because of the negative, and the square root of 4 is 2. So there's our 2i. Over here, if we add the 4 over to the other side, x squared equals 4. Let's square root both sides. Don't forget your plus or minus. Cool that we end up getting the exact same answers, but a much shorter way, huh? But it's kind of neat to use this new knowledge that we have to get the same results. All right, you guys. So our synthetic division really getting used to help us break down these polynomials to higher degrees, that we don't have things like the AC or the quadratic formula, right? These degree 3, degree 4, degree 5 polynomials, we can chip away at them and reduce them by doing synthetic division with some given zeros, or if we weren't given zeros, using that rational zeros theorem where we take factors of the last over factors of the first and try all those. All right, you guys. So good luck on the homework. Thanks for joining me.